So here is Handbrake theorem. This theorem says that E be a subspace of X and let F naught belongs to E star, then there exists an extension F belongs to X star such that F restricted to E is equal to F naught and norm of X star F with respect to X star equal to norm of F naught with respect to E star. Generally, an extension theorem means you're having a set. Suppose I'm taking the set as A and it has got a subset. That subset I'm taking as B. Okay. Now the extension theorem means you have got a function from B to some set C. Okay, so this is my F. Now if I can define a capital F from A to C such that f of x is equal to f of x is equal to f of x for every x belongs to B. Okay, now here I can define some other thing, that is something like f of x plus some x, second function now. So if I can define like this, only specialty is that when you're finding your capital F of x, it should be the same as small f of x for every x belongs to B. That means we can extend this from the set A to C like that. This is capital F and we will write this as F capital F restricted to B is equal to small f. So this is the general extension idea. Now for Handbrake theorem, I told it is also called Handbrake extension theorem. Handbrake extension theorem. So what does this theorem says is that you have got your x star. So x star means, suppose this is your x and this is your real valued function, real or complex. Anyway, I am taking this to be as a real valued one. Oh, sorry. Okay, so here got a real valued or a complex valued function over here. So this is my, if I am taking this to be as real valued, because in this chapter we are dealing only with the linear spaces over the real values. Okay, now from here you are having the linear bounded linear functionals. Okay, so these are going to be my, from here I am taking a subset. The subset is called E. I am having this F from E to R. So I will write here I am having F from E to R. So I can say that this F belongs to E star. Okay. Now I can extend this F belongs to E star to from X to R as some capital F. So here we have denoted as F naught. Okay. So here is F naught and this is going to be a small f itself. Okay. So we are having F naught from E to R. That means F naught belongs to E star. Now this can be extended to an F from where to where? From X to R. That means this F belongs to X star, I can say. in such a way that our restriction was f restricted to E star should be equal to f naught. And one more condition is given: norm of f in x star should be the same as norm of f naught in E star. Then we will say that this f is a Banach extension of your f naught, okay, to x star. Okay, so we have extended your f naught to the entire space x star. So now we come back to the theorem. E be a subspace of X and F naught belongs to E star, then there exists an extension F belongs to X star such that F restricted to E is equal to F naught. That is, F of X is equal to F naught of X for all X belongs to E, and norm of F with respect to X star equal to norm of F naught with respect to E star. Now we are not going to prove here. The norm is same means the meaning is you have studied your norm for 5 equivalence conditions, equivalent definitions. So I am taking one from that. That is supremum of mod f of x, x not equal to 0 and x belongs to x by norm of x equal to supremum taken over x belongs to e and x not equal to 0 mod of f naught of x by norm of x. Okay, now in this chapter I have said we are defining only on real line. All spaces are defined over real line only. Now here comes the corollary 1, 3.1a corollary. For all x naught belongs to S of x, where S of x is the unit circle or the unit sphere, there exists f naught belongs to x star such that norm of f naught with respect to x star equal to 1 and f naught of x naught equal to 1. So the functional f naught at is supremum on the unit ball on the vector x naught. Okay. So this theorem says, so the corollary says that you have got your unit sphere here centered at 0. Now here you have got an x naught, then there exists an f naught belongs to x star. So here is called, you have got something like this. You are having an x over here, so this is your x. Now from x to your real line, you are having an x star. Okay, so here we have got an f or f naught. Now this f naught belongs to x star. F naught belongs to x star such that norm of f naught of x star equal to 1 and f naught of x naught, this x naught, okay, this is equal to 1. So we want to prove that first thing is norm of f naught of x star equal to 1 and further is f naught of x naught equal to 1. Okay, for that you consider an x naught belongs to s of x, that's equal to set of all x belongs to x such that norm of x equal to 1. Now we will consider the one-dimensional subspace E naught. E naught is equal to lambda x naught, okay, where lambda belongs to real line. We define the functional phi of lambda of x naught is equal to lambda. Okay, so phi of 3x naught means 3 will come. Now we will find the norm of this phi. So norm of phi over E star equal to, by our definition, supremum x not equal to 0 and x belongs to E modulus of phi of x naught by norm of x naught. See, from here you can see easily that the supremum will become 1. Reason is we are finding a phi of x naught. Phi of x naught means phi of 1 into x naught, right? So phi of x naught will become 1 by definition. Phi of lambda x naught equal to lambda. So phi of x naught will become 1. Now you take modulus of phi of x naught, you will get 1 only. Now again you are taking x belongs to E. What was your E? E was set of all x belongs to R such that norm of x equal to 1, right? Equal to 1 or less than 1. Yeah, equal to 1. So you taken this equal to 1 only. So you get this entire quantity 1 by 1. So supremum x not equal to 0, x belongs to E, 1 by 1 will get as 1. So you get norm of phi of E star equal to 1. Now what we can do? We can directly apply our Handbrake extension theorem to this function phi, right? Now you are having your phi belongs to, by Handbrake extension theorem, there exists an extension of phi, say phi dash. Now the speciality of phi dash is phi dash belongs to x star, and by Handbrake theorem, norm of phi dash x star should be equal to norm of phi in E star. This was the first condition, right? So this will become now 1. Okay, so this is the case equal to 1. And also we have x phi dash of x naught. Phi dash of x naught means again this x naught belongs to E, then phi dash of x naught is equal to phi of x naught, that is equal to 1. Now phi dash of x naught is equal to 1 we will get. Thus phi dash is the desired function s naught. So hence the corollary. Now we will pass to the next corollary. Corollary 3.1.5. For all x naught belongs to x, there exists f naught belongs to x star minus 0. That means there exists a non-zero functional f naught such that f naught of x naught equal to norm of x naught into norm of f naught. So for all x naught belongs to x, there exists some f naught belongs to non-zero f naught such that f naught of x naught is nothing but norm of x naught into norm of x naught. So proof is like this. Again we will consider the unit sphere. We take an x naught belongs to x. Now clearly when you are having x naught belongs to, so taken an x naught belongs to x. Now if you are having x naught dividing with its norm, and if you are taking norm of this means evidently this norm is equal to 1. That means x naught by norm of x naught belongs to s of x. Okay, now we can apply the previous corollary. Okay, so from previous corollary we have got an f naught belongs to x star such that norm of f naught with respect to x star equal to 1, and f naught of x, that x naught equal to 1 we have got. So f naught of x naught by norm of x naught should be equal to 1. For this equation as 1 and this as 2. Now from 1 we will get norm of f naught of x star equal to 1, which definitely implies that f naught not equal to 0. If f naught equal to 0, you will get this norm as 0. And from 1 and 2, what you will get is, from 1 you have got this, and from 2, so I can conclude that f naught of x naught by norm of x naught is equal to 1. Instead of 1, I can replace that 1 with norm of f naught, right? Now, if this is the case, f naught is a linear one. So I can have this as 1 by norm of x naught into f naught of x naught equal to norm of f naught, right? So for the multiplying, cross multiplication, you get f naught of x naught equal to norm of f naught into norm of x naught. Okay, so that's the case here. So from 1 and 2 we get f naught uh, of x naught by norm of x naught equal to norm of f naught with respect to x star. That is f naught of x naught by norm of x naught equal to norm of f naught x star. That is f naught of x naught equal to norm of x naught into norm of x naught. So we have proved this corollary also. We have to go through few more corollaries of this Handbrake extension theorem. So this much of corollaries arising means you might have noticed that the importance of Handbrake extension theorem. So we will prove the theorem in the 9th chapter, but the corollaries we should study now itself and the statement of the theorem. Okay, so I'm closing today's session. Thank you for your patience. Thank you. So before starting, remembering Handbrake extension theorem, the Handbrake theorem says that if you are having let E be a, so I'll write here. So Handbrake theorem over here. Let E be a subspace of X. So I'm writing in this fashion, subspace of X, and F naught belongs to E star. F naught belongs to E star. Then there exists a function or extension X belongs to X star such that, so F naught belongs to E star, then there exists an F belongs to X star such that condition is norm should be the same and f should be the extension. So we are having f restricted to E is equal to f naught and norm of f naught is equal to norm of f. So norm of f in x star is equal to norm of f naught in E star. This was our Handbrake, sorry, not E star. This was our Handbrake theorem. Now we are passing to corollary 3.15. So what does this corollary says? For all x1 belongs to x and for all x2 belongs to x such that x1 not equal to x2, that means x1 and x2 are two distinct elements from your space x, then there exists an f belongs to x star satisfying f of x1 not equal to f of x2. Okay, so its idea is that we will say that two elements x1 and x2 given idea is this two elements this x1 x2 belongs to x and x1 not equal to x2, so definitely there will be a difference, that is x1 minus x2, this will be belongs to your space x. And we will say that sum x0 is equal to x1 minus x2. We want to prove that f of x1 not equal to f of x2 such that one f is existing there. Okay, then by previous corollary 3.14, what we will get is there exists an f naught. So by corollary 3.14, right? 3.14, there exists and f naught belongs to x star minus 0, that means non-zero functional, such that f naught of x naught is equal to norm of x naught f naught into norm of x naught. So this follows from our previous corollary. Now instead of x naught, you can apply your x1 minus x2. So you will have f naught of x1 minus x2 is equal to norm of f naught into norm of x1 minus x2. Now since the norm of f naught is great, this quantity is greater than 0, we get f of x naught minus, so f naught x x1 minus, since it is linear, f naught x2 is equal to 0 if and only if norm of your x1 minus x2 is equal to 0. Am I right? Which implies if norm of this equal to 0 implies this condition follows from the fact that you have got an f naught in non-zero linear functional. Therefore, its norm should be always greater than or equal to, not equal to, norm is always greater than, so norm of f naught is always greater than 0. Now this quantity equal to 0 means only possibility is that norm of x1 minus x2 should be equal to 0. If norm of something equal to 0 implies that equal to 0, that is, which implies x1 minus x2 equal to 0, which implies x1 equal to x2. Okay, but given x1 not equal to x2, therefore what you got is, therefore f of x1 cannot be equal to f of x2. Okay, let us see the proof in detail. Since x is a linear space, x1 x2 belongs to x means x1 minus x2 is also belongs to x. Say x0, something like that. From previous corollary, you will have this condition. Now, instead of x0, you can apply x1 minus x2. Now, since your norm of f0 is always greater than 0, f of x1 minus f0 of x2 equal to 0, if and only if norm of x1 minus x2 is 0, which implies x1 equal to x2. But given x1 not equal to x2, therefore f of x1 cannot be equal to f of x2. So what is this? This follows if x1 equal to x2, f of x not equal to f naught of x2. That is the thing you want to prove. Okay. So hence the corollary. Now we will move to next corollary. Corollary 3.16. X star is a total set. Okay. The statement is very precise. X star is a total set, meaning that if f of x equal to 0 for every f, then x is equal to 0. Okay, what you want to prove is if f of x equal to 0 for every f, then x equal to 0. So it proves, this proof is like this. From proof of corollary, from previous proof, I will write, from previous proof of 3.1.5, that's just before what we have discussed. We have equation star, we have a condition f naught of x naught is equal to norm of f naught into norm of x naught. So equation star, we mark this as equation star. Now assume that, now you assume that, now assume that your f of x is equal to 0 for every x. So f of x equal to 0 for every f. Therefore, in particular, you will get f naught of x naught is also 0, right? F naught of x naught equal to 0, which implies norm of f naught into norm of x naught is equal to 0 for every f. For every f. See here, for every f, this quantity is equal to 0, which implies in particular you can take this f as the identity function also. Okay, no, sorry, not identity function. You can have some scalar or multiple or something like that. Okay, since f naught is a linear function, I was not supposed to take the identity function, but instead of that, I can take this as a constant multiple function and all. Non-zero constant multiple, then I cannot find that its norm is 0 and all, right? So this is true for every f naught, means only possibility is that x naught should be equal to 0. Okay, since we can find, since we can find f naught belongs to x star such that condition is, sorry, such that your norm of f naught not equal to 0 for at least one f naught should be there. So which implies norm of x naught is equal to 0, right? Which implies your x naught is equal to 0. That is, if f of x equal to 0 for every f, then that is if f of x equal to 0 for every f in x star, then x is equal to 0, which implies x star is a total set, is a total set. Okay, now we will pass to corollary 3.1.7. This corollary says that let L be a subspace of a normed space X, and let X belongs to X such that distance between X and L is equal to D. That means you are having your X over here, this is your X, and somewhere here you have got your L. Okay, now you have got an element X belongs to X somewhere here, and the distance between this X and L, this distance is D, which is greater than 0, so X. Then there is a system f belongs to x star such that norm of that linear function will equal to 1 and f of L equal to 0 and f of x equal to D. So you want to define an f in x star such that norm of that function should be equal to 1 and its value in L is 0 and its value in X is the distance between X and L. So first of all we will consider uh, a set L1 that is equal to span of X comma L. Now L1 is nothing but lambda x plus y such that lambda belongs to R and y belongs to L. Now we take an element z belongs to L1. So z can be written as lambda x plus y. Now define a function f naught of z is equal to lambda d. Define the function f naught of z is equal to lambda d. Now f naught is well defined. For well defined, what you want to prove is if you are having z1 equal to z2, now we want to prove your f naught of z1 is equal to f naught of z2. If we can prove like this, means we can say that the function f naught is well defined. Now you take your z1 and z2 from your zl1. So z1 is of the form lambda 1 x plus y1 and z2 is of the form lambda 2 x plus y2. Now suppose z1 equal to z2, that is lambda 1 x plus y1 equal to lambda 2 x plus y2. Therefore, the distance between x and L is greater than 0, right? And y1, y2 belongs to L. Now you can define this well defined. If z1 equal to z2 means you get this quantity is equal to this quantity. And y1, y2 belongs to L and distance between x and L is greater than 0. That means they does not have any intersections. Right? So we will have lambda 1 equal to lambda 2 and y1 equal to y2. So this implies that f naught of z1 equal to lambda 1 d and f naught of z2 equal to lambda 2 of d. So lambda 2 of d can be replaced with lambda 1 of d. So this implies that f naught of z1 is equal to f naught of z2. This altogether implies that your f naught is well defined. Now we want to prove this f naught is linear. This is as our usual custom, we will prove as in the same way as a linear transformation is linear. So we should consider f naught of z1 plus z2. This you can easily follow, it's going to be linear. And next I will consider, instead of this you can already consider f naught of mu z1 plus some rho z2 and prove the linearity. I have proved in two ways, that is two steps I have proved. F naught of z1 plus z2 I have proved that is equal to f naught of z1 plus f naught of z2, and f naught of mu z1 is equal to mu into f naught of z1. So definitely this f naught will belongs to L hash. What was L hash? The space of linear functional on L. Now f naught of L is equal to 0. The reason is the distance you have taken for defining your f naught of lambda x you have defined as lambda d, right? So you are taking this distance. So whenever you are considering your set L itself, we should measure the distance from L to the set L. So definitely that distance should be 0. So f naught of L is 0 and f naught of x should be equal to d. Since f naught of x I am finding, f naught of x means f naught of 1 into x it is. So by definition it is d into 1 will come, that is d alone. Now what we have to do? We have done up to this. There should be a further step. A further step is to apply the Handbrake extension theorem. Okay. Now for z is equal to lambda x plus y, you can have mod of z is equal to lambda x plus y. Before that we should prove that norm of that function is equal to 1. Okay, so you're taking norm of z. Norm of z by definition, norm of lambda x plus y. If you're taking the lambda quantity outside, this will become mod lambda into x plus y by lambda. So this is equal to mod lambda into norm of x minus of, this I can write it as x minus y by lambda. So this quantity is greater than or equal to mod lambda into infimum of, this is exactly the distance between x and L, right? So I can replace that with infimum, so the inequality becomes the inequality greater than or equal to mod lambda into infimum of dxy such that y belongs to L. So this will reduce as mod lambda into d, because this distance means it is d. So that is equal to mod of f naught of z. So you have got mod of z is equal to mod of greater than or equal to mod of f naught z. But when you consider the norm of f naught means you have got a quantity mod of f naught, see here, mod of f naught z by norm of z. Now we have got norm of z is greater than or equal to mod of f naught of z. That means the value of this quantity is always less than or equal to 1. Now again you are finding the supremum of a quantity which is less than or equal to 1. So its supremum is also less than or equal to 1. So I can arrive the conclusion that here the norm, when you're finding the norm of f naught, norm of f naught should be always less than or equal to 1. Of course, you have found the distance between x and L to be 1. Then we can evidently find the elements yn belongs to L such that yn belongs to L such that norm of x minus of minus yn is equal to x plus yn, which converges to d. Hence, you can write your d as d is equal to modulus of f naught x plus yn, which is less than or equal to norm of f naught into norm of x plus yn, which converges to d into norm of f naught. From where I got this one? See here. So when this n tends to infinity and all, we will have this quantity remains the same. That I have written as it is norm of f naught. Now what about this quantity? Now as n tends to infinity, norm of x plus yn, this quantity will tend to d. See here, this quantity will tend to d. So I will have the quantity as d is equal to d into norm of f naught. Since you know that norm of f naught is evidently greater than or equal to 0, right? But now you got the inequality or the equality as d, and this tends to d into norm of f naught. So the possibility is that f naught cannot be equal to 0. So only possibility is that norm of f naught should be greater than or equal to 1. Just previously you have got norm of f naught is less than or equal to 1 here, and here norm of f naught is greater than or equal to 1. So we can conclude that norm of this f naught is equal to 1. Okay, now we can apply the Handbrake extension theorem to f naught. Then applying the theorem, you will get there exists an extension f of x naught such that norm of f with respect to x star is equal to norm of f naught with respect to L1 star. Therefore, norm of f should be equal to 1, and since it's going to be the extension, its restriction to L should be the same as f naught, and f of L should be equal to f naught of L, that should be equal to 0, and f of x is equal to d itself. So we have proved the corollary. Okay, so today I'm stopping. I'm winding up this session. Thank you for your patient listening. If you feel any clarification for the unit admins, just post your comments or your queries in the group or in the classroom. Thank you. Thank you for your patient listening. Thank you. Handbrake extension theorem. Okay. So Handbrake extension theorem says that whenever you are having a subspace E and if F belongs to E star, then it has got an extension to X star such that you will mention it as capital F such that the capital F is defined from, you got your capital F that is defined for capital F, which can be considered as if it restricted to E star, then it should be your small f or f naught we have mentioned. And what else do you have? You have got one more condition. Norm of f at x star is same as norm of f naught at E star. So this was their Handbrake extension theorem. Now with this we are having one definition. For any L subsets of X, the annihilator, okay, will denote it as L pub. In linear algebra also you have studied what is an annihilator. So we have got a subset L, subset of X, and it is defined as L pub is equal to or annihilator of L. So let me denote it as annihilator of L is equal to set of all f belongs to x star such that f of L is equal to 0. So definitely your L pub or the annihilator of L is a subset of x star. Okay, but you are taken L subset of x, but your L annihilator is always a subset of x star. Now L star or what is the annihilator of L is a closed subspace of X. So annihilator of L is a closed subspace of X star. So how to prove it? For closed subspace we want to prove that first of all L pub or annihilator of L is a subspace. So how to prove it's a subspace? For proving subspace means we want to take two elements. So let me take as f comma g belongs to L pub and alpha beta scalars. And what I want to show is alpha into f plus beta into g of some x. I want to prove this as 0. Then only I should take some x belongs to L also, right? So x belongs to L. Now if I am proving alpha into f plus beta g of x equal to 0, which implies that my alpha f plus beta of g belongs to the annihilator of L. Does it follow? Can you follow it? Yeah. So just we are proving that it's a subspace first. Then after that we will prove that this subspace is closed. So let's see how we can prove it. So we are assuming that L not equal to empty. If L equal to empty means evidently we'll get the result. So we are defining annihilator of L as set of all f belongs to x star such that f of x is equal to 0 for every x belongs to L. Now thus L perp is a subset of the device space x star of x. Okay, this we have already discussed. So it's a subset already discussed. Now L perp is a subspace of x star. For that, as I have told, we should take alpha beta scalars fg belongs to L perp. It is okay. L perp. Okay. Now consider for every x belongs to this, you will have alpha f plus beta g of x equal to, since f and g are linear, alpha into f of x plus beta into g of x. Now this become f of x and g of x for x belongs to L. These two quantities will be zeros. So alpha into 0 plus beta into 0. So everything will come as 0, which implies your alpha f plus beta g belongs to your annihilator of L. Therefore, your annihilator is a subspace of X star. Now we want to prove that this L annihilator of L is a closed subspace. See, purposefully I am not reading it as L-perp because L-perp you have already defined the set of all those vectors which are orthogonal to L, right? So here we should read it as annihilator of L. So annihilator of L is a closed subspace. So for that what we have to go is you will consider an F belongs to closure L or annihilator of L closure. If this is belongs to closure means by definition you know that there exists a sequence Fn in annihilator of L such that condition should be your Fn converges to F. Now we want to prove that this F belongs to your annihilator. If you are proving this, we will say that your annihilator is a closed space. Okay, I repeat, you take an F belongs to annihilated closure, then by definition, if something belongs to closure means there exists a sequence which converges to F. So here we have got a sequence Fn in annihilator set such that this sequence converges to F. Therefore, F is belongs to your annihilator. Once you are proving this, you will get your annihilator set is closed. Okay. So you take F belongs to annihilator's closure, then there is a sequence of bounded linear functionals in annihilators such that limit n tends to infinity Fn is equal to F. Therefore, for x belongs to L, limit n tends to infinity, Fn of x is equal to f of x. But Fn of x equal to 0 for every x belongs to L. Since your Fn belongs to annihilator set. Therefore, for every x belongs to L, you are having your Fn of x is nothing but zeros. Now, as limit n tends to infinity, your Fn of x is again should be 0. But this is by definition is equal to f of x. So what does this follows? Your f is also belongs to your annihilator set. So which implies your annihilator set is closed. So we have proved that your annihilator is a closed subspace. Now here is three remarks. First remark, when you're finding the annihilator of x itself, so when you're finding annihilator of x, the entire space, so you will get f belongs to x star such that f of x equals 0 for every x belongs to x. So whatever the function you will consider, you want to get it as f of x equal to 0 for every x belongs to x. For every x belongs to x and for any functional this should be true means only one possibility is that your f should be equal to the 0 operator. Am I right? Now for any 0 operator, if you're finding f of x for every x belongs to x, that would result u0. You have studied that a linear function is another special case of linear transformations and all linear transformations maps 0 to 0. Okay. So when you are finding annihilator of x means it is nothing but the zero operator. Be cautious when I am writing singleton zero, it means it is the zero operator. Now conversely I am finding what's the annihilator of zero means. In this means it is a subset, right? So annihilator of this subset. Here what I am considering is singleton 0 is a subset of x, but here it is the 0 operator. Now if this is the case means I want to consider those f for which f of 0 is equal to, oh, I have written a mistake here. This is exactly, I'm writing somewhere space. Okay, no problem. So here I will write this. This is exactly if I want to find this annihilators of 0 means it is set of all f belongs to x star such that my f of 0 is equal to 0 because only one number is there, that is 0. Now, if I am finding f belongs to x star such that f of 0 is equal to 0, this is nothing but I will get the entire f, right? So, it is nothing but x star. So, you make here correction. So, here is a mistake. So, this is exactly your f of 0 is equal to 0, right? So when I am finding the annihilator of the entire space, I will get it as in zero operator. And if I am finding the annihilator of singleton zero, I will get the entire space x term. Now here is one more result. If I am finding closure, that means annihilator's closure, it will be the same as annihilator of L. This follows from two facts. One fact is that annihilators of L is contained in annihilators of L closure, right? Since A is contained in A closure, in the same way, here you are having annihilators which is contained in annihilators closure. Okay, and further we have proved that now L annihilator is a closed. So annihilator is closed and annihilator's closure is a closed subspace again. So this is going to be the maximal closed subspace, right? So only possibility is that your annihilator should be equal to the closure of the annihilators. Okay. Now the third remark is you take an F subset of your X star. So in F means F is a subset of linear function, okay, bounded linear function. So f itself is a collection of functions. Now if I am finding its annihilator, I will get f belongs to, previously it was x star, now I am taking the membrane x star, so x star star such that f of x equal to 0 for every x belongs to x star. See, now here x belongs to x star. Now I will have this as such that f of some x of t equal to 0, right? Because x itself is a function. For every x belongs to x star, I can modify it. But if I am writing like this, so it's enough to find for x of t equal to 0, because if x of t equal to 0 means f of 0 will result 0. So I can rewrite this as set of all x of t belongs to, or x belongs to x star such that I'll have x of t equal to 0 for every t belongs to x. So in same way I can define it like this. So we are making use of this. Now from previous result, this is a closed subspace of X star star. Now it can also define, as I said earlier, so X belongs to X such that, so I have written X belongs to X star. Okay, so here's a mistake. So I will have this as X belongs to X itself. So X belongs to X such that, so I should have, oh, so I will rewrite it. This I have written wrongly. So I'm so sorry. I have written this wrongly. So from here, see, okay. From here, you see here that if you are having f of x of t equal to 0, then definitely, if x of t equal to 0 means definitely your f of x should be equal to 0. So we need to find those t for which your x of x belongs to x star, x of t equal to 0. So this can also written as set of all t belongs to x such that your condition should be x of t equal to 0, right? So x of t equal to 0 for every x belongs to x star. So this can be modified like this. So using this, we can write this as another notation I am following. So this is equal to set of all x belongs to x such that f of x equal to 0 for all f belongs to f. Since you have taken f, I have taken here x star. So you have taken f, so all f belongs to f. Now this is called the dual annihilator. So this is called the dual annihilator. Dual annihilator. So dual annihilator of f, we will denote it as f or dual annihilator of f, that's equal to set of all x belongs to x such that f of x equal to 0. See here, for all x belongs to f. If it is for all f belongs to f, f of x equal to 0 means evidently it belongs to kernel of f for every f. So it will belongs to the intersection. So we have intersection of f belongs to f, kernel of f. So it is called the dual annihilator. So we have defined annihilator of a set and dual annihilator also. So for the coming problems, we will have only this definition. We don't follow the previous one. That means dual annihilator. We had defined it in two ways. One way we were defined in this version, that is in this one. This is the one we have defined, but we are not making use of this definition here, but we will make use this definition. Okay. Now here is the corollary 3.1.8. Let L be a closed subspace. Consider the subspace annihilator of L, and consider annihilator of L its dual annihilator. Okay, that is x belongs to x such that f of x equals 0 for all f belongs to annihilator. Then the result says that when you are finding the annihilator of L and its dual annihilator, you will get it as L. I repeat, when you are finding annihilator's dual annihilator, it will result L. That is dual annihilator of dual annihilator of annihilator, right? Dual annihilator of L is nothing but L. So this is the corollary. Dual annihilator of L is L. So we want to prove this. See, these two are going to be two sets. So we will prove one is a subset of another. So for that, first you will prove L is contained in annihilator of L, dual annihilator. So let X belongs to L. Then by definition, for any F belongs to the annihilator, we have f of x equal to 0, which implies x belongs to kernel of f for any f belongs to annihilator. For any f belongs to annihilator means definitely this x belongs to intersection of kernel of f belongs to the annihilator. That means by definition this is dual annihilator of annihilator. So x belongs to the dual annihilator of L. That implies your L is contained in dual annihilators, right? So we have proved one way of inclusion. Now to prove the other way of inclusion. For this, we will prove that exactly we want to prove that if some y belongs to dual annihilator, then your y belongs to L we want to prove. Instead of this, we will prove that if y does not belongs to L implies y does not belongs to the annihilator, dual annihilator, right? So if we can prove this, it is enough. Okay, we will say that contrapositive and all. So we want to prove this. For that, what we will prove is if x does not belongs to L, then x does not belongs to the dual annihilator of the annihilator. So let x does not belongs to L. Then L is closed. So we will have the distance between x and L should be always greater than 0. Then we can make use your corollary 3.1.7. That corollary says that if this is the condition, that is if x belongs to x and x does not belongs to a closed subspace L of x, then the distance between x and L is greater than 0, means that's equal to d. If d equal to distance between this and this is greater than 0, then there exists an f belongs to x star such that norm of f is equal to 1 and f of l equal to 0 and f of x equal to d. So we can take that f here. Now we will have f of l equal to 0, which implies f belongs to the annihilator of L. And further f of x equal to d, which is not equal to 0, which implies f of x not equal to 0 for f belongs to the annihilator set. That means x is not in the kernel of f if f belongs to the annihilator of L. That means x is not in the intersection of f, kernel of f, where f belongs to the annihilator set. That means x is not in the, so that implies x is, by definition this intersection means nothing but your dual annihilator of annihilator. That means your x is not in the dual annihilator of annihilators. That means you are having your dual annihilator of annihilator is contained in L. So we should conclude that your dual annihilator of annihilator is nothing but your L itself. Hope you can follow it easily. So with this, I'm closing today's session. Thank you for your patience. Thank you. So here is the remark. Let X be a Banach space and X star is the dual
Consider the dual space x star star, double dual you are considering of x star, which is denoted by x double star. Now x may be identified with the subspace of x double star in the following way. So x and x double star can be identified. For x belongs to x, consider the functional ix belongs to x double star such that for every f belongs to x star, ix of f equal to, so we are defining this like this. We are having ix of f is equivalent to or is equal to or identically equal to f of x. We are defining this map from x belongs to x. So we are having here what x is there, here is your x star, and you have gone for x double star also. Okay, now from here we take one x, here one f, next you are finding f of x over here. So this is a ix of, so here what is coming is ix of f. This defines a map I from x to x double star. So there's a map I from x to x double star. Now this is a one-to-one linear map. So we will prove first of all I is linear. Our usual method, let some x comma y belongs to x and alpha beta belongs to f is R or C. Now consider p of alpha x plus beta y of f. By definition, it is f of alpha x plus beta y. Since f is a linear functional, we are having f is linear. So it will compose as alpha into f of x plus beta into f of y. Now this is nothing but f of x you can replace with ix of f and f of y, iy of f. Therefore I is linear. Now I is 1 1. Now consider we want to prove I is linear, we have proved. Now we want to prove I is 1 1. So in order to prove I is 1 1, I am taking kernel of I. So kernel of I when I am taking, I should get set of all x belongs to x such that ix of f equal to 0 for every f belongs to x star. So for every f belongs to x star, I should have ix of, see here, ix of f is equal to 0 implies, by definition, this is f of x equal to 0 for every f belongs to x star, which is possible only when my x should be equal to 0. So I will get the singleton set. Whenever this is a singleton set means you have studied that this linear transformation or the linear function is 1 1. So which implies my I is 1 1. Now for any linear functional we have modulus of f of x is less than or equal to norm of f into norm of x. So in particular our ix of f is also less than or equal to norm of f into norm of x. Call this as your equation 1. Now what should be the norm of ix in x star star? So it should be I of x is equal to, again using the idea of our operator norm definition, supremum f not equal to 0, ix of f by norm of f. So this is equal to supremum f not equal to 0, ix of f by definition is f of x. So modulus of f of x by norm of f. But from here we are having, from here from equation 1, so from 1 implies I'm writing as it is. Ix of f its modulus value is less than or equal to norm of f into norm of x. But Ix of f is nothing but modulus of f of x. So modulus of f of x is less than or equal to norm of f into norm of x. So when you are taking this, you are having modulus of f of x by norm of f, if f not equal to 0, is less than or equal to norm of x. So when you are having supremum over your f not equal to 0 of this quantity mod f of x by norm of f should be less than or equal to norm of x, right? So this quantity is less than or equal to norm of x we got. Now from corollary 3.1.3 of Handbrake theorem, we have the supremum is attained at some point. Okay, so we will have for any x there is some f not equal to 0 such that modulus of f of x is equal to norm of x into norm of f. Okay, so what you will have? So modulus of f you have found it as supremum f not equal to 0 modulus of f of x by norm of f. This is your norm f. But norm f is equal to, you can replace that with maximum of f not equal to 0 mod f of x by norm of x. But this quantity you have already seen that this is equal to norm x. See here, less than or equal to norm x you have shown, but by 3.1.3 of Handbrake theorem, the supremum is attained at some points. Therefore, at some points x should be equal. That means this norm of f should be equal to norm of x. So what does this mean? This means that the map I from x to x double star is an isometry. So we will say that it's an isometry into. So if there is an isometry means we will say that the map is, there is an isometry I from x to x double star. So that means that we can identify your x and x double star. Okay. Now here's one more definition. If the map I is onto, we will say that that is into map. So suppose this I is an onto and the space x and x star are isomorphic in a natural way. That means if you can identify this, so if this I is onto, that means we can identify x and x double star. So this is only next definition says. So this will lead to the definition of some space called reflexive spaces. Okay, so this will reduce the definition of a reflexive spaces. So next is that definition. If the map I is onto and the spaces x and x double star are isometric in a natural way by the map I, we call such spaces reflexive spaces. Thus, in reflexive spaces, we need not distinguish what was this? Annihilators, right? Annihilators of f and annihilator of dual of f. Hence, you have identified this to be as the same. Okay, so this remarks can be asked as a question also. What was the question? Can you frame the question from this remark? See, X be a Banach space and X star is dual. Consider dual space X star star of X star star. Now X may be identified with a subspace of X star, they are asked. Instead of that, why called a subspace of X star? Since it is not mentioned that it is an onto one. So if there exists, or you may be asked to show that X star, whenever X is a Banach space, X star is dual, and now X is identified with a subspace of X star star. That is in one way, or in another way means by defining an onto function, or they can ask like this also. Let Ix from X to X star be an onto function, be an onto, then show that X and X double star can be identified. Can be identified. So identified means we want to prove an onto isometry with the condition norm of f is equal to norm of x. If this is the condition existing means we will say that these two spaces can be identified. Okay. So with this I am closing today's class. Thank you for your patient listening. Thank you.
So in previous class you have studied about the map. That map is given by let X be a Banach space and X star is defined. Now for the map is like this. For X belongs to capital X, consider the functional. Consider the functional I of X belongs to, so it's defined from X to X double star is defined as for every f belongs to f star, for every f belongs to x star having ix of f is equal to f of x. This we have seen in the last class remark. Now we have defined that this map from I to, now we have proved I is linear and I is 1 1, linear 1 1, and further you proved that this will define an isometry, right? So 1 1 and I is an isometry into. Now coming back to this definition. Now if the map I is onto, we have proved that it's up into only we have seen. So suppose the map I is onto and spaces, now we can say that now I is an, so our I is a linear isometry onto. So suppose this is a linear isometry onto, then you can have the map from x to x double star, right? Then you can identify these two spaces that this definition says. If such a map is existing means we will say that these two spaces are reflexive. Okay, let us see the definition. If the map I is onto and the spaces x and x star star are isometric in a natural way by the map I, we call such spaces reflexive spaces. So in reflexive spaces, you can have here the orthogonal, not orthogonal, the annihilators, right? So the annihilators of as we have seen, this is the linear isometry from x to x star star. Now you are having this thing denoting as annihilators, right? So first you denote the annihilators like this, and this annihilator you are denoting as x star stars annihilator you are denoting as uh, x like this. Okay, now we can identify these two because there is a linear isometry from x to x double star, so the annihilators will be the same, right? So that saying here. Thus, the reflexive spaces we need not distinguish f annihilators of f and annihilators of dual of f. Okay, can you follow the definition of reflexive spaces? First, we are having space x and x double star. Now you define I of x from x to x double star defined as for every f belongs to x star, ix of f is equal to f of x. Now this f is linear 1 1 and in isometry onto we will say that the spaces x and x double star are isometric and the spaces x and x double star are called reflexive spaces. Definition of reflexive spaces. Okay, can you? I think now it's clear. So reflexive spaces means you will be able to find an I from x to x double star with the condition I is linear, I is 1 1. Now I is onto next one, I is a linear isometry. Then if these all conditions are false, then we will say that x and x double star are reflexive. So that is the definition of reflexive spaces. Now here is an example of a dual spaces. You consider space C0. C0 means a set of all sequences which converges to 0. So C0 of null sequences with the norm of x equal to maximum of mod f(ai), x equal to a1, a2, a3, etc. Now we define a linear functional f on f by fixing a sequence bi belongs to L1 and setting the action of this sequence on x belongs to C0 by f of x equal to sigma ai phi. Now this you have studied in your Rees representation theorem. So Rees representation theorem, we studied that if some f belongs to x star, then this f can be identified with an element y belongs to the same space such that norm of f is equal to norm of y and all. Okay, so we can identify this f with y. Now here what I have taken is I'm considering C naught. So set of all sequences which converges to 0. Now I'm taking an element x belongs to C naught. Now x belongs to C naught means I am having my x as a sequence, some a1, a2, a3, etc. Right? So this is my sequence. Now I'm defining the norm on x as norm of x equal to maximum of mod ai. Okay, now with this I'm defining a function f such that f of x is equal to for that I'm fixing an element bi. So if b, the sequence b belongs to L1, I'm taking my f of x as sigma. So b1 means it is of the form some b1, b2, etc. So this form is your b1. So with that, I'm defining my f of x as f of x equal to sigma ai bi. Okay, up to this we have seen. Now what we have to do is you consider norm modulus of f of x. So it's not clear here, right? During scanning, just come like that. I think the enter page is like this. Okay, no problem. So then we are having, you find what is the modulus of this one. So modulus of this means modulus of this. Okay, so modulus of f of x is my f of x. Modulus of this value is less than or equal to sigma modulus of aix bi, that is sigma modulus of, I will write it here, that's equal to sigma modulus of ai into modulus of bi. Now we can replace this with maximum of ai, that's equal to or less than or equal to maximum of mod ai into bi. Now you can take this maximum outside. So we get maximum of mod ai into sigma b mod bi. Now maximum of mod ai we have defined it as norm of x at c naught. So I'm writing this norm of x at c naught into what is sigma of bi by Reverse representation theorem. It is, you have seen that when you are fixing like this, means by Reverse representation theorem I have mentioned earlier. So Reverse representation theorem, we are having this norm of f is equal to norm of y you will get. Okay, so if you are using that here means you can replace this sigma mod bi with norm of f at L1 because your b belongs to L1. Okay, so b belongs to L1 and b is equal to b1, b2, etc. Now consider the one norm over here. So norm of b1 means, sorry, norm of b means b1, norm of b means in L1 norm is sigma I equal to 1 to infinity mod bi. Okay, so this is the norm. That means this entire quantity is nothing but your norm of b. Now by representation theorem, norm of b at L1 I am writing. So norm of b at L1 is same as norm of f at L1. So I can replace that with norm of f at L1. Now what is follows is, see, modulus of f of xi. So this implies that when you are taking this supremum also, this value should be less than or equal to this quantity. So I can have this quantity, that is supremum of, so I missed that one here. So therefore supremum of mod f of xi by norm of xi, right, should be always less than or equal to this norm of x at c0 into norm of f at L1. So this implies this quantity is nothing but norm of f at C0. The norm of f at C0 is C0 star is less than or equal to norm of f at this L1. Call this as your equation 1. Now let we want to get the reverse inequality also. So now let f belongs to C0 star. En belongs to C0. That is your En equal to, as in our usual terms that we are taking, this one occur at the nth place, remaining all values 0. Now you define your f of En as Bn. So you're defining f of En as Bn. Now you take yn equal to sigma k equal to 1 to n e power minus I into argument of bk into ek. Now you have studied in your complex classes. When you're taking norm of this means I will get exactly 1. Okay. So this value is equal to 1. So we are taking in yn's value at c0 and the norm defined over c0 is norm of x is equal to defined as maximum of mod ai, right, where x is equal to a1 a2 etc. So this is the case, you define norm like this. Now in this case, if we are taking norm of this means you will get norm of sigma k equal to 1 to n e raised to minus I into argument of bk into ek time. Now you can have the modulus of this value is 1 and this value is also 1. So we will get it as 1. And for any n belongs to n, we have norm of c0 star is greater than or equal to f of yn. Now f of yn is nothing but this value. Okay. Now which implies norm of f at c in c star is greater than or equal to norm of bi at L1. Now we can replace it. So now identifying f belongs to c0 star with a sequence f equal to bn belongs to L1, we get norm of c0 star is greater than or equal to norm of f at c0 star is greater than or equal to, see here you have got it as norm of c0 f at c0 star is greater than or equal to b1. Now you can have this f identified with b's, right? So you'll have norm of f is greater than or equal to c0 star is greater than or equal to norm of f at L1. Now this is the equation 2. This follows from reciprocation theorem, and from 1 and 2, what is your 1? Here 1 was norm of f at c0 star is less than or equal to norm of f at L1. Now here you have got it as norm of f at c0 star is greater than or equal to norm of f at L1. Now from these two quantities we will have norm of f at c0 star is equal to norm of f at L1. Okay. So we have got this quantity. Thus we can identify L1 as the dual space of C naught. So we are having here L1 as dual space of C naught. That is L1 is equal to C naught star. Okay. So we have got L1 is equal to C naught star, which is addition preserves norm. Okay. So this norm preserves addition. Okay. I think I have taken only a few things only today. So what is the reflexive space? The next one, example of a dual space. Okay, so you have found the dual space of C naught star, sorry, dual space of C naught, and found that that is equal to L1. Okay, so you have proved that C naught star is equal to L1. Okay, we have to go through a few more examples and some problems that we can do in the next class. Okay, thank you for your patient listening. Thank you. Discussed in your last class. So an operator, first of all, the definition of a dual operator. So the operator we are denoting as A star is called the dual operator. Dual operator to the operator A, to the operator A where A star is defined from Y star to X star, and recall that A is defined from X to Y. Okay, and norm of A star is equal to norm of A star is equal to norm of A. So this is the condition. Okay, and one more condition is the say that phi of A star for some phi belongs to Y star. So this condition is when your phi belongs to or phi or phi belongs to Y star, then phi of AX is equal to or equivalent to A star phi of X. Thus we will say that A star is a dual operator of A. Now in today's class, first of all we have discussed some example of such a dual operator. So example, consider k t tau belongs to L2 I2, I equal to close interval 0 1, and define the operator k on L2 of close interval 0 1 by kx of t equal to integral 0 to 1 k of t tau into x of tau d tau. So you are defining your k of x in this fashion. Now the adjoint operator k star is given by k star y of t equal to integral 0 to 1 k of t tau bar is conjugate into y of tau d tau. Here
k star y of tau. We want to prove this. So we will prove that the adjoint operator of A is this one. We have the inner product of kx and y is equal to, by definition, it is kx, k of kx into integral. By definition, this is nothing but integral over 0 to 1 k of x into y dash dt form, right? Where y dash x dash of t, this also t will come. Okay, so this is the general norm. Sorry, general inner product. So instead of k of x, we can replace k of x with the value. So I have replaced that. So this is the value of your k of x. So this is your kx. So kx of t, I can say kx of t into y dash y of t bar dt. Now this is equal to integral 0 to 1 x of tau. See, x of tau I am taking outside, means this is with respect to the integration is with respect to tau. So x of tau into whatever is remaining, integral 0 to 1 k of t tau y of t conjugate dt. Now this is equal to integral 0 to 1 x of tau into, I can write this double conjugate, right? So at last it will have integral 0 to 1 x of tau into integral 0 to 1 k of t tau conjugate, exactly y conjugate will come, so it is conjugate alone, sorry, y of t alone, and dt is all conjugate, right? All conjugate into dt, that's equal to inner product of, what is this now, x into y star, I can write, where y star means this entire quantity. Okay, so I have written from where you started kxy, I'm getting as xy star, where y star is equal to integral 0 to 1 k of t tau conjugate into y of t dt. This is the thing asked, because in the previous class we have seen that whenever you're having a conjugate of this type and conjugate of this type, you have proved that this is equal to, in terms of you have proved in terms of f only. So a star phi is equal to f. The starting of the class itself I have mentioned what is the condition. So we will get the adjoint of k is this quantity. Now a theorem is the theorem 4.1.1, 4.4.1. A from x to y is compact implies A star from y star to x star is compact. Now we want to prove that A star is compact. So proving compactness, we will use Arcelo's theorem. So in order to prove A star is compact, we will show that A star d of y star is y star. Now what is d of y star? D of y star denotes the unit ball in y star. Okay, so A star of d of y star is equal to k, which is contained in x star, is pre-compact. So the idea is that in Arcelo's theorem we have proved some result that saying that if we want to prove A is compact, it is enough to prove that A of the unit ball is pre-compact. So if you are proving this, we can say that A is compact. Okay, so it is in the reverse order, right? So I should erase this. It is on the reverse order only. That means whenever this is occurring, we can say that A is compact. So A is compact. Okay. Now for proving this is pre-compact, we want to prove this one is bounded and A is equicontinuous. Okay, so Arcelo's theorem. Now d of y star denote the unit ball in y star. So let f belongs to a star d of y star. So f belongs to a star d of y star. Then f of x is equal to a star phi of x for some x belongs to d of x and some phi belongs to d of y star. That is f of x is equal to a star phi of x. That's equal to phi of a of x. Okay. Also, norm of f star equal to supremum norm of x less than or equal to 1 modulus of f of x, that's equal to supremum over norm x less than or equal to 1. F of x is same as, see here, f of x is same as phi of x. So I can replace that with phi of ax. Now this will reduce as supremum y belongs to t, modulus of phi of y. Why this is, I can write like this? Since if y belongs to t, what will happen? What was t? T is a of dx. Okay, which is pre-compact in y since A is compact. So consider the collection of continuous functions on T. That means M is equal to phi belongs to d of y star. So any phi belongs to d of y star. We have modulus of phi of y is always less than or equal to norm of A. Okay, can you follow this? Modulus of phi of y is always less than or equal to a. What is you are taken as m and phi of y? See, y belongs to t. T means a of dx. That means the unit balls contained in x, right? So a into a d of x we are considering. So this value should be always less than or equal to a for y belongs to t. And phi of y1 minus phi of y2, which is less than or equal to y1 minus y2 into norm of phi. It's clear? Now since phi belongs to d of y star, then f belongs to y star such that norm of f is equal to 1. So that is the condition. It's unit ball. We get this norm of phi should be equal to 1. So we get modulus of phi of y1 minus phi of y2 is less than or equal to y1 minus y2. So whenever your y1 y2 minus norm of y1 minus y2 is less than delta, what you are getting is norm of or modulus of phi of y1 minus phi of y2 is also less than epsilon, where epsilon is equal to delta. So that's the condition. So this quantity is also less than epsilon. And this condition implies your phi is equicontinuous, right? So whenever norm of y1 minus y2 is less than epsilon. So this implies, first of all, we have proved that this is bounded. See here, this is bounded. Phi is bounded. Now here we have proved that phi is equicontinuous. For that, from these two, using Arcela's theorem, we can get M. What is was M? M means the set of all phi belongs to d y star is pre-compact. Okay, this is pre-compact. Now let Fn n equal to 1 to infinity be a bounded sequence in A star d of y star. Now from equation 1, we get the corresponding sequence of function. What is 1? See here, f norm of f star is less than or equal to supremum modulus of y of phi of y, where y belongs to T. So from the equation 1, we get the corresponding sequence of function phi n, where n equal to 1 to infinity is also bounded, right? And hence there exists a subsequence. Since this phi n is going, we have proved that it is pre-compact, so it should have a Cauchy subsequence. So phi n dash such that this is the condition of Cauchy sequence. Norm of phi n dash minus phi n double dash tends to 0 as n dash and n double dash tends to infinity. Then by condition 1, we will get this quantity is less than or equal to, this quantity is less than or equal to norm of phi n dash minus phi n double dash, right? Now this tends to 0 as n dash and m dash tends to infinity. That means fn dash minus norm of fn dash minus fn double dash tends to 0 as n dash and n double dash tends to infinity, which implies your A star, since this is the sequence you are taken in your A star, so A star is compact whenever A is compact. Okay, so this should also have a subsequence which is Cauchy. That means your A star is compact. Okay, so I'm closing today's session. Thank you for your patient listening. Thank you. Dual operators. In linear algebra class 2, you have defined what is dual of an operator. So what was that? If you're having any idea means, we will revise that and we'll start. So we will denote that as X star. Now X star means set of all F belongs to L, X, F. That means F can be real number or complex numbers. So it is the set of all linear functionals from X to the field. So here we are defining the linear uh, dual operators. So consider A from X to Y be a bounded operator and let phi belongs to Y star. That is, meaning I have written phi from Y to F. Then f of X we are defining as phi of A of X for X belongs to X. Now define a linear function on X. This is a linear function on F. Now moreover, to find what is a linear is very easy to prove because phi belongs to uh, your y star. Okay, so phi belongs to y star means it is a linear functional. So linear function already is given. So no need of checking if the linear function or not. Now we want to prove that this is bounded. For that you take norm of f of x. So norm of f of x is equal to a mod of f of x, that is mod of phi of ax. So this value is less than or equal to, we can split. So norm of phi at y star into norm of a into norm of x. Okay. This in two steps we can do, but I have done in only one step. So exactly will come as this is less than or equal to norm of phi of at y star into norm of ax at ax is defined from x to y now. So y. Next case you can split this in this version. Okay. So what does this means? This all are bounded now. So this is also bounded. Thus we get f belongs to x star. Hence, we have a map P to F. That is, the map will map P to F. Let's have written here clearly. That is, there is a map A star from Y star to X star, such that A star of phi is equal to F for phi belongs to Y star. Now A star is linear because A star is defined as A star of phi is equal to F, and F we have already seen that it is linear. So this is linear. Next we want to prove this is bounded. Okay. So for every x belongs to x and phi belongs to y star, we have phi of x equal to a star phi of x. Definition: nothing else. A star phi of x. See here, a star phi of x. Y star containing your phi. So a star phi means it belongs to uh, x star, but it is mapping uh, see phi to f. So I can write this as f of x, but f is given as, see, f is a star phi. So I can write this as phi of ax, which is same as a star phi of x. Now a star is a bounded operator. That means that I want to prove norm of a is less than infinity, or which is finite. Now norm of A is defined as supremum norm x equal to 1 norm of A of x in y. Now I can write this in this version also. If I am having this is in y, so I can have norm of phi is equal to 1. That means somewhat identity operation. So I can replace this with phi of A of x. So this I can write as supremum of norm x equal to 1, supremum of norm phi is equal to 1, modulus of phi of A of x. Now this is equal to supremum of norm of phi equal to 1 into supremum of norm of x equal to 1, modulus of phi of A of x. That's equal to supremum of norm of phi equal to 1, supremum of norm of x equal to 1. This is same as previously we have written. This is same as a star phi of x. So modulus of a star phi of x. Now this is equal to supremum norm phi equal to 1 into this quantity means it will result the norm of a star of phi. So this is supremum norm phi is equal to 1 norm of a star phi at x star, and this is nothing but norm of a star. So what you have proved is you started with the norm of a and you have proved that equal to norm of a star, since a is a bounded operator, right? So norm of a star is equal to norm of a implies that norm of a star is also bounded. That is, a star is a bounded operator. So this implies the operator A star is called the dual operator to the operator A is also bounded. So now dual operator to the operator A. Also note that A star is defined from Y star to X star. So here the dual operator is defined as, suppose you are having an operator A from x to y. If you are having a linear map, then its dual A star is defined from y star to x star. Okay, with the condition that norm of A star is equal to norm of A. Such an A star is called the dual operator to the operator A. Also note that A star is defined from y star to x star. Now we will follow some notation. The notation is that generally we will write the function of x as f of x. But here we are following the idea xf. Instead of writing f of x, we are writing xf. That's the first notation here. So let X be a normed linear space and X star its dual. For F belongs to X star and X belongs to X, we denote the action of F on X as XF instead of F of X. Okay, that is XF is same as, I should write in this version, same as your F of X. Okay. Xf is same as f of x. See here, even though we are having the inner product notation over here, it is entirely different from the inner product. The reason is that the first one, this x belongs to where? X belongs to, I have written x belongs to x, but where this f belongs to? F belongs to x star. So these two elements came from two different sets. But in inner product means these two should come from a same space. So it is different. One, a general linear space E and a space of functional f on E. F may not be E star. We call XF the pairing between E and F. So this is called pairing between E and F. Now note 2. See, just before what I have said, even though we use the same notation of inner product for pairing, it should be noted that in pairing, the first and second argument belongs to different spaces. Now, applying this notation to the pairing between x and x star, we can rewrite the definition of dual operator A star of an operator A in the following way. For all x belongs to x and for all f belongs to y star, AXF. That means, its meaning is that f of AX, right? This is same as, I should write A star f of x. Okay, so f of x is same as A star f of x. This we have seen. So remark 1, if A belongs to L of xy, that is a linear operator from x to y, and B belongs to L of yz, then B A star. Okay, that's equal to A star B star. Now A star B star is defined from Z star to X star. Okay, when you find the dual of a product, it should be equal to dual of each of that in the reverse order, right? So in case of Hilbert spaces for operator, if A belongs to L of H1, H2, that is H1 and H2 are Hilbert spaces, you will say that adjoint operator. So A star is called the adjoint operator in case of Hilbert spaces. A star, which is defined from or which belongs to the linear space of H2 to H1, is defined by the relation AXY equal to X A star Y, for X belongs to H1 and Y belongs to H2. So remember this, AXY is equal to X A star Y, and here A star in case of Hilbert spaces we will say that adjoint operator. Okay, with this I am closing today's session. Thank you for your patient listening. Thank you. So this is called the shift operator in L2. You know that in L2 the element should be, okay, in L2 you are having the elements in L2 you're having elements as your x1, x2, x3, etc., xn, etc. So of infinite type. Now, bounded linear operator we are defining as a shift operator means if t is a shift operator, you can say that if this is a x, then t of x is defined as first element I am fixing as 0, then x1, x2, etc., xn, comma, etc. Now, this is called the shifting operation. This you may come across many times, so I am not going in detail. In R2 and all, it will exactly give you what is called the shift. That means each point you are shifting to uh, the point whose first coordinate is 0. That's t of x is given as like this. Now this is a bounded linear operator, since the reason is that in L2 when you are calculating norm of x, exactly this is in L2. Okay, norm in L2, and this is again norm in L2. Okay, so when you are having the first coordinate, mod of that square means a 0 square will come. So t of x and x both should have same norm. Also we know that norm of tx is less than or equal to norm of t into norm of x, but both sides are equal means t should be equal to 1. Norm of t should be equal to 1. That means t is a bounded linear operator. It's a very simple one to say in your Viva also. Whenever you are asked to give an example for a bounded linear operator, you give L2 space. In L2 space, you define the shift operator. Okay. Next is the fifth one. Alpha ij I comma j equal to 1 to infinity be an infinite matrix, and let k square, we define that as sigma I equal to 1 to infinity and j equal to 1 to infinity modulus of alpha ij square, which is finite. Then the operator a defined in L2 by, we are defining this as a of alpha I from I equal to 1 to infinity is equal to beta I. Now what is beta I? So exactly here there is a correction. So you can take this to be as alpha is equal to alpha 1, or else I should find some alpha I means better to put alpha. That's better. Alpha. Then again I is coming, right? So alpha I. Let it be alpha I. So what I should do? Okay, you put alpha I is equal to alpha I1 because it's a member in your L2 space. That's why alpha I2, etc., alpha IN, etc., like that. Your alpha I means it is of this form. Now A of alpha I is equal to beta I. The meaning is that, see, when you are finding this means you'll get beta I means j equal to 1 to infinity alpha ij into alpha j for I belongs to n. So here alpha ij and all means j means this only. Okay, this for I, now this for j. So j means this will come 1, 2, etc. up to n will come. Since this notation is not given here, I am not specifying that, I will go for alpha j for I belongs to n. Is a bounded linear operator. So in order to prove that this is a bounded linear operator, in your textbook it is given that check that this value is less than this. So let us check that. So beta I, modulus of beta I means modulus of alpha ij into alpha j will come. So that value means which is less than or equal to sigma j equal to 1 to infinity alpha ij square raised to 1 by 2 into sigma j equal to 1 to infinity alpha j square raised to 1 by 2. Now this quantity for alpha equal to, I have put alpha equal to alpha 1, alpha 2, etc. because I am not so much comfortable with this notation that I have mentioned earlier, that is alpha I equal to 1 to infinity they are giving. So here the problem is that your alpha I belongs to L2. Okay, now in L2 means it should be of sequence. So I will have alpha I1, alpha I2, etc. But here again they are fixing that as something like this. So in order to avoid that, the better thing is that you can have alpha is equal to, I will write here, once you are fixing your alpha equal to alpha 1, alpha 2, etc., alpha n, etc., and you are defining your a of alpha. So there should be no confusion. A of alpha is equal to beta I. Okay, now beta I should be equal to something like this. Then it is valid. Okay, now beta I is equal to sigma j equal to 1 to infinity alpha ij into alpha j you have defined. Okay, now mode of beta I. So mode of beta I means mode of this thing alpha ij into ij. Now this can be split up into less than or equal to sigma. This is alpha ij. Okay, alpha ij it is modulus of alpha ij it is square. Okay, raised to 1 by 2 into sigma j equal to 1 to infinity alpha j square raised to 1 by 2. Now this will result exactly the norm in norm of alpha it is, right? Now for alpha equal to x alpha 1 alpha 2 etc., we will have norm of a alpha square, that's equal to sigma I equal to 1 to infinity mod of beta I square, and this value just we have seen that this is less than or equal to this value. Now this quantity will reduces as norm of alpha square. So what you're getting is norm of alpha square into sigma I equal to 1 to infinity sigma j equal to 1 to infinity norm of alpha ij square, and that's equal to this quantity is given, we have assumed this to be as k square. So k square into norm of alpha square. So we can conclude that norm of a alpha is less than or equal to k into norm of alpha 2. Okay, so this part is not given in your textbook. Now we are going for the sixth example. Let H be a separable Hilbert space and let I equal to 1 to infinity be an orthonormal basis. Let A from H to H be a bounded linear operator. Now we have these two conditions we have studied whenever it's the orthonormal basis is given. In your section 2 you have studied this. So we can write A is equal to ax is equal to sigma I greater than or equal to 1 a inner product of ax into ei, and x can be written as sigma j greater than or equal to 1 xj ej, where xj is equal to xej. Now from 2, since a is bounded operator, a is a bounded operator, we have ax is equal to sigma j equal to 1 to infinity x ej into a of ej. What you are proving here? It's a bounded linear operator is given Hilbert space. Then orthonormal basis you have considered a is a bounded linear operator, and from this, since a is bounded, we will get a of x is equal to this quantity, and substituting a of x in your equation 1 for this a of x we are substituting, we will get this ax is equal to sigma I greater than or equal to 1 sigma of this expression as such I have substituted. Now from this expression will reduces as sigma like that x ej into ej. This is all you have know already. Now let eij ei I am putting as aij. Thus I will get this equal to x equal to sigma xi ei and y equal to sigma yi ei and y equal to ax. Okay, thus we get yi is equal to sigma j greater than or equal to 1 aij into xj. Now the sequence alpha I is mapped by a to beta I. This just as what you done in your exercise number, sorry, not previous example 5. But the problem is that here it doesn't give the condition that some k square less than infinity. I don't know. That condition is not given here. So hence the sequence alpha I is mapped by A to, sorry, is mapped to A to beta I. Consequently, the operator A defined by the matrix, so you can go for the matrix notation of A, but however, example 5 may not be applicable since that I have already said that the k square is less than infinity is not usually satisfied. So in this case also, you can have A as a boundary linear operator. How you fix your A? H to A given by, it's a linear operator given by Ax is equal to Ax Ei into Ei. Okay. Now our conclusion is that will it form the operator A defined by the matrix, however, may not be applicable. That means Ax cannot be applicable here since it is not given that this condition. What is it? Yeah, this condition k square into alpha square. No, it's given that. Yeah, this condition is not given in the last exercise. So this is not true. So with this, I'm closing today's class. Thank you for your patient listening. Thank you. So here is example 2. In L2 of closed interval 0, 1 and 4, in L2 of closed interval 0, 1 and 4, an element A of L2 of closed interval 0, 1 square, L2 I square we will write. Define the operator K from L2 0, 1 to L2 0, 1 by K f of t is equal to integral 0 to 1 k t tau into f of tau d tau. Now this function k t tau tau k of t tau, this we will say that kernel or the kernel function. Okay? So our function is defined as k from L2 closed interval 0, 1 to L2 closed interval 0, 1 such that k f of t is equal, this is t, k f of t is equal to integral 0 to 1 k of t tau f of tau t tau. Now the function of two variables k t tau is called the kernel or the kernel function of operator k. Now we want to prove that this is a linear operator. Let us denote the operator of k by operator norm, right? So now we want to prove that this norm is less than or equal to this. That means this is bounded, right? So we will prove this. Consider the norm over L2 I2. I means closed interval 0, 1. I means closed interval 0, 1. So consider the norm over there. In L2 of closed interval 0, 1, you know the norm is integral 0 to 1 of modulus of the function into dt. But here we are having I cross I. That is, we have to go for two integration, that is integral 0 to 1, integral 0 to 1 modulus of k of t tau square d tau dt. So call this equation as your star. So your star mark equation. Now you consider norm of kf square. Norm of kf square means is modulus of what is kf? Kf just before you have defined as integral 0 to 1 k of t tau f of tau d tau. Now this square. Now this is equal to integral 0 to 1 into integral 0 to 1 of this thing, right? Now this quantity is less than or equal to integral. You can take this modulus to here I missed the modulus it seems. No. Norm means you are getting the integral signs. Okay. Now this thing is less than or equal to modulus of this thing. That means I can replace that integral 0 to 1 modulus of k of t tau into f of tau d tau square into dt. I am writing this means I can apply the Holder's inequality or the Cauchy-Schwarz inequality. Now next step I am using that. Now I can see that this will reduces as integral 0 to 1 k t tau modulus of that square d tau all thing raised to 1 by 2 into integral 0 to 1 mod f of tau square d tau all thing raised to 1 by 2 all square dt. Now this quantity is less than or equal to integral using Cauchy-Schwarz inequality. This will represent norm of f, right? So this will reduce as norm of f and this as h I am writing. Now I can take this norm of f outside. So norm of f square will come into integral 0 to 1 k of t tau square d tau raised to 1 by 2 here whole thing raised to square dt. Okay. Now this quantity is less than or equal to norm f square into integral 0 to 1 modulus of k of t tau modulus of square it should be modulus, right? So here means modulus is the square into d tau dt. Now this is equal to norm f square into, this is nothing but we have seen this is the starting itself we have noted that this is this norm by star. Now we will see that this quantity is this one. That means your operator norm of k is less than or equal to k t tau into L2 I. It means this is a linear operator. See, when you are taking this norm means you should consider supremum and all. But you have taken from that, you have taken only one element, kf. Okay? Supremum over f not equal to 0, mod norm of kf only you should consider when you are taking this norm. So supremum values always should be less than or equal to this quantity. That means this is a bounded linear operator. Now the third case, let kt be a continuous function on closed interval ab. In L2 of ab, define the operator a by af is equal to k of t into f of t. Sadly, this is small k. So k of t into f of t. Then a is a bounded linear operator. Linearity very easily follows. So just we want to prove that it is bounded. And norm of a is equal to m for maximum a less than or equal to t less than or equal to b modulus of k of t. Now we have norm of af means you're taking supremum over norm f of t equal to 1, norm of k of t into f of t you can have. That means you can have here the maximum value, right? And f of t equal to 1 means this value should be norm should be always less than or equal to maximum value. Maximum value is m. Okay, so see this maximum value. So we have one side of the equality, that's norm of a is less than or equal to m. Now what we want to prove? We want if we can prove that suppose we can prove that the other way. So this we have proved. This if we can prove that this m value is less than or equal to norm of a, then it is proved, right? Now to show that norm of a is equal to m, suppose m is equal to k of t naught. Okay, so maximum value is attained at naught. Now define a sequence xn in by xn of t equal to root of n by 2. This root is entire root. You can put a bracket over here. Let's see. Okay. For t belongs to t naught minus 1 by n and t naught plus 1 by n and 0 otherwise. Now just to calculate what is norm of xn. Now norm of xn in L2 means integral over t naught. In entire integral will come, but this value is 0, all other integrals except this range. So we will have the integral from t naught minus 1 by n to t naught plus 1 by n. At the stage xn's value is root of n by 2 square into dt. Right? Now go for the integration of this part. You will get the integral as 1. A simple integration. I not explain here. Just you do the integration. You will get that to be as 1. Now by continuity of k of t, we assume that k of t is continuous. We assume that k of t is continuous at x naught 2. So what is follows is you find your norm of a xn square. By definition, it is integral t naught minus 1 by n to t naught plus 1 by n modulus of k of t into root of n by 2 square dt. Okay. Now this is equal to, you can write this as n by 2 into this into modulus of k of t. Now you take whenever t tends to t naught. Exactly, meaning is that n tends to infinity. Then only your t value should tends to t naught. Okay. So for t tends to t naught, what you will have? This t will become t naught. Right? Now the remaining means integral t naught minus 1 by n to t naught plus 1 by n. So you put this in bracket. No need of specifying it here. Into integral n by 2 dt will come. Right? Now what is that? N by 2 dt. Just before you have proved that to be as equal to 1. See, this exactly this quantity only will come there. Now you will get this as, see, n by 2 into this will come, that is k of t naught square into n by 2 into this, that is this equal to 1 by equation star. So whatever you are getting is norm of, sorry, modulus of k of t naught square. So you proceed with here. That means a norm of a xn square converges to modulus of k of t naught square. And we know that norm of a square is should be always greater or equal to norm of a xn square. And this converges to k of t naught square, which implies norm of a is greater or equal to modulus of k t naught. But modulus of k t naught means it is nothing but your m value, maximum value. Let's call this as equation 2 from equation 1. What was that? It was the equation 1. So from equation 1 and equation 2, you can conclude that this value norm of A is equal to M. That's why we have proved that this operation is a bounded linear operator. Okay, so I'm winding up today's class. Thank you for your patient listening. Thank you. So last class we had discussed the space of compact operators, a proposition, a set K from X to Y of compact operators from X to Y satisfy K of from X to Y is a linear subspace of L of XY. This we have already proved in the previous class, and today we will prove if A belongs to K of XY, that is A is a compact linear operator and B is a linear bounded operator and C is again a linear bounded operator, then AB, the product, is compact linear operator. Similarly, CA is also a compact linear operator, and in this case if x equal to y, it means that AX is a ideal, right? It's a two-sided ideal of L of xy, sorry, L of x's. And the third one, Kx to y, that is this compact linear operator is a closed subspace of set of all bounded linear operators. So, passing to result 2. If that means, again I have explained, if A is a compact linear operator, B is a bounded linear operator. First thing we want to prove that AB is a compact linear operator. So consider the operator AB from Z to Y. Let Zn n equal to 1 to infinity be a bounded sequence in Z. Since B is bounded, B of Zn is also bounded when A is compact. Hence, consider A of B of Zn, the sequence. This has a converging subsequence. Now take that convergent subsequence as, okay. Now consider the operator BA. Okay. Let set xn, sorry, the sequence xn be a bounded sequence in X. Let xn be a bounded sequence. Oh, it's a repetition, so no need of one line. One line you can skip. Okay. Now A is compact, hence the sequence A of xn n equal to 1 to infinity has a converging subsequence. Let that convergent subsequence be A of x and k. Now since B is bounded, it follows that the sequence B of A, x and k is also converging, and thus BA is compact. Exactly, we have proved that this is pre-compact, which implies that BA is compact. Similarly, you take CA. So CA belongs to K of x to y, Z. Now, if K of x is equal to this, you replace Z with x itself, we can say that this is a compact linear operator from x to x. This Kx is always a subset of Lx. And for A belongs to Kx and B belongs to Lx, AB belongs to Kx and BA belongs to Kx, which implies Kx is a double-sided ideal. An ideal means we will say that N is an ideal of G if for every A belongs to G, An is contained in N. Right? Similarly, two-sided means when you are taking NA, this is also should be contained in N. Then we will say that this is an ideal. Now here you have proved that kx is an ideal. That means when you're having an element from, see, you have writing here, you consider Lx and Kx. Now Kx is an idea. You take an element from here, you took you B from here. From here you have taken an A, and you have proved that BA is belongs to Kx. Right? Again, you took some element over here, and you have proved that AC is belongs to Kx. That means this Kx is an ideal. Now we will pass to the next statement. That is K from x to y is a closed subspace of L of x to y. For closeness, we want to prove that it contains all its limit points. That means if I am having a sequence an which converges to a, I want to prove that this a also belongs to kxy. Okay, so let an belongs to k from x to y, and an converges to a. Now we want to prove that a belongs to kxy. That is, a is compact. For that, let dx be the unit ball. Dx be the unit ball. We must prove that A of dx, the image of unit ball, is pre-compact. This we have already proved. Means if this is the condition, means operator A is compact, right? Thus, we have to find for all epsilon. For that, what we want to prove? We can talk in terms of epsilon nets. Okay, we want to prove that there exists a finite epsilon net for A of dx. Now for all epsilon greater than 0, there exists n belongs to n such that norm of an minus a is less than epsilon by 2. This follows from the fact that an converges to a. Now since an is compact and d of x is bounded, then an of dx is compact. N is compact and d of x is bounded, N of dx is pre-compact. Again, we are using the same condition. Now take an epsilon by 2 net yi from 1 to n of an dx. Then you consider yi 1 to n is an epsilon net for a dx. Thus, for any y belongs to a of dx, this follows from the fact that yi, okay, epsilon by 2 net is yi. Now an converges to a. Therefore, this yi is served as an epsilon net for a dx. Thus, for any y belongs to a of dx, there exists x belongs to dx such that y equal to ax. Since yi from 1 to n is an epsilon by 2 net of an dx. Now take your yi naught from the net such that norm of yi naught minus anx is less than or equal to epsilon by 2. Okay, you select such a yi naught. Consider norm of y minus yi naught, which is norm of that should be less than or equal to a of x, because y means a of x. Okay, and you introduce an x and subtract that anx. It doesn't make any change. Now you can split this. It is less than or equal to norm of ax minus anx plus norm of anx minus yi naught. Now this we have seen that this is less than epsilon by 2, and you have selected an yi naught such that this condition is satisfied. So this quantity is also less than epsilon by 2, so that is epsilon. That means this yi naught will form an epsilon net. And this yi naught is finite because yi from 1 to n. Okay. We have proved that this is a closed subspace. Okay. It's a closed subspace of Lxy. So with this, I'm closing today's session. Thank you for your patient listening. Thank you. The same thing, that is lemma 4.3.3. Let M be relatively compact if and only if for every epsilon greater than 0, there exists a finite epsilon net in M. And last class we have seen that one part of this we have proved. So assume that there exists an epsilon naught greater than 0 such that there is no finite epsilon net of M. There exists no finite epsilon net of M. Then take an x1 belongs to M and choose x2 belongs to M such that norm of x1 minus x2 is greater than or equal to epsilon naught. Now select an x3 belongs to M such that we have gone constructing an sequence xi I equal to 1 to n minus 1. Now we have proved that this sequence distance between this is greater than or equal to epsilon naught. Now such x and exist, and since okay, thus the sequence is not a Cauchy sequence. That means no sequence of xn is a Cauchy sequence, which implies M is not pre-compact. So we have proved that part. Now to prove the converse part, conversely means what do you want to prove? M has a finite epsilon k net for every k. We want to prove that this is compact. Okay. Now to prove the converse, for all k belongs to n, take an epsilon k less than or equal to 1 by 2k. So we are selecting our epsilon k is less than or equal to 1 by 2k. Now assume that M has a finite epsilon k net for every k. Assume that M has a finite epsilon k net for every k. Now take a sequence xn n equal to 1 to infinity in M and consider a finite epsilon 1 net. So now any xn belongs to some balls around the net points. So there is at least one ball which contain an infinite subsequence. Reason is that the sequence is something like this, means which contain infinite numbers, right? So when you are having the epsilon balls, it should be something like this. Then there exists at least one ball. More than one ball is possible, but anyway there should exist at least one ball which contain infinite number of elements. See here, this set contain infinite number of elements. So at least one ball should be there which contain infinite number of elements. So this is a sequence. Now if you are having the epsilon nets, at least one will contain infinite number of elements. So there is at least one ball which contain an infinite subsequence of from the original sequence. Now this subsequence be xn. So this here whatever is coming, this you are mentioning as xn 1 from n equal to 1 to infinity. Okay. Similarly, if we consider an epsilon k net, we will get a subsequence. Epsilon k net, you are considering epsilon 1 net, and when you consider epsilon k net, again you will get a subsequence. Okay, this epsilon k net divide the sequence between a finite number of balls, and there is a one ball which contain an infinite subsequence of the previously chosen sequence. Now we will take this subsequence as x and k. So when you are having epsilon k net also, you will have so many epsilon balls, something like this, and at least one epsilon ball which contain infinite number of elements. So this is the infinite number of elements set. In that you take the subsequence as x and k minus 1 or x and k. Okay, this is x and k. Now the radius of the ball is less than epsilon k. Clear? Hence, for all m n belongs to n, what you are having is this quantity xm raised to k minus xm raised to k is less than or equal to 2 times epsilon k. So which is less than or equal to, we will have 2 times into 1 by 2k it will be. So 2 will get cancelled, you will get this as 1 by k. What does this means? It's a Cauchy sequence, right? That is the subsequence of xn n equal to 1 to infinity is a Cauchy sequence. Now indeed, for all eta greater than 0, we can choose v belongs to n such that 1 by v is less than or equal to eta, right? So it is always possible that xn raised to n minus xm will be always less than or equal to 1 by v, which is less than or equal to eta. Since both vectors belongs to xi of v, which implies m is relatively compact, should have a Cauchy subsequence, so it is relatively compact. So m is relatively compact. So what we have proved is m is relatively compact if and only if for every epsilon greater than 0 there exists a finite epsilon net in m. Converse part, we have proved that whenever there exists a finite epsilon net in m, then m is relatively compact. For proving relatively compact, we want to prove that it should have a Cauchy subsequence. Now we are passing to the next topic, the space of compact operators. And the first proposition over there, let's set k from x to y of compact operators from x to y satisfy these properties. That is, k of x to y is a linear subspace of L of xy. Second condition, if A belongs to k of xy and B belongs to L of zx, then C belongs to L of yz, then AB, the product belongs to k of zy and CA belongs to k of xz. K means k of xy means set of all compact linear operators from x to y. Then L and zx means set of all linear operators from z to x. Okay. So let us see one more condition is there that we discuss in next class. First we will prove the first condition. That is, we want to prove k xy, that is the set of all compact linear operators, is a linear subspace of L of xy, that is the set of linear operators. So let us take, we will prove this in your usual procedure only. That is, the thing is that we will consider some f and g. For the namesake, I am taking this as k and this as l, and lambda and mu belongs to the field. Now we will prove that lambda f plus mu g belongs to k. Then this will be a compact linear operator. Now for proving lambda f plus mu g belongs to k, what you want to prove is compact. That means it should have a what do you want to prove? This lambda f plus mu g of some xn which is bounded, and this is a Cauchy sequence we want to prove, right? So for every bounded sequence xn in X, the sequence fxn and gxn have a Cauchy subsequence. Follows from fg belongs to k of x to y. Now consider lambda f plus mu g. We want to prove lambda f plus mu g belongs to k of x to y. Consider the sequence lambda f of xn. Since fxn has a Cauchy subsequence, say, take it as fxni, such that f of xn minus f of xm is less than epsilon whenever your n and m is greater or equal to ni. Now, if lambda equal to 0 means there is nothing to prove, right? 0 less than epsilon always it should be. Now, if lambda not equal to 0, we can select our epsilon as epsilon by mod lambda. Then what will happen? Then consider modulus of lambda f of xn minus lambda f of xm. Now, you can have this lambda common. Then taking outside, you will get mod lambda into modulus of f of xn minus f of xm. Now, this is mod lambda into this quantity is less than epsilon by mod lambda. Since f is going to be, f belongs to k x to y, it is compact, right? That means f of xn minus f of xm should be less than some epsilon. But here we have selected our epsilon as epsilon by mod lambda. So this is valid. So what you are getting is this is less than epsilon, which implies lambda f xni is a Cauchy subsequence or lambda f is compact. Now similarly, we can prove that mu g is also compact. Now consider lambda f plus mu g of xn. Since lambda f of xn has a Cauchy subsequence, take that Cauchy subsequence. Again, we are having mu g of xn is again have a Cauchy subsequence. Say that subsequence as mu g of xnj. This is xni and this is xn. Now take your nk to be the maximum of ni and nj. Okay, and you consider modulus of lambda f plus mu g of xn minus lambda f plus mu g of xn, where n and m are greater than or equal to nk. Now by definition itself, you can have lambda f plus mu g of xn as lambda into f of xn plus mu into g of xn. So we have splitted that. Now this is equal to lambda into f of xn minus f of xm plus mu into g of xn minus g of xm, which is less than or equal to, again you can split this into modulus of lambda into f of xn minus f of xm plus modulus of mu into g of xn minus g of xm. Call this as equation 1. Since lambda f of xni is a Cauchy sequence, we have lambda f of xn minus f of xm is less than epsilon by 2 for n comma m greater than or equal to nk. Again, mu g of xnj is a Cauchy sequence. So we are having mu into g of xn minus g of xm is again less than epsilon by 2 for all n comma m greater than or equal to nk. Therefore, for n comma m greater than or equal to nk, this equation will become modulus of lambda f plus mu g of xn minus lambda f plus mu g of xm is less than epsilon by 2 plus epsilon by 2, that is epsilon, which implies our lambda f plus, this is f, plus mu g of x and k is a Cauchy sequence. That means your lambda f plus mu g is a compact operator, or which implies lambda f plus mu g belongs to k of xy, which implies your k of xy is a linear subspace of L of xy. Okay, thus we have proved the first part of the lemma or the property. So in the next class we will prove the other two properties. Okay, so today I am closing. Thank you for your patient listening. Thank you.
Last class we have seen three examples, and here is the fourth example. It says that let k t tau be a continuous function of two variables on closed interval 0 1 cross 0 1. 0 1 cross 0 1 means nothing but we're having in R2 cross R2, I'm going to have cross R2, you will have this one. Okay, this is 0 1, this is 1. So this is the domain. Okay, now you define kx is equal to integral 0 to 1 k of t tau x tau d tau. This is defined from C of closed interval 0 1 to C of closed interval 0 1. Now this is a compact operator. So how to prove it? So first of all, let us state M is equal to set of all x of t be a bounded set of functions from C of closed interval 0 1 such that norm of x is less than or equal to r. Now consider the function y of t is equal to integral 0 to 1 k of t tau into x of tau d tau, where x of t is a function from M. Now we can note that this function is of two variables k, t, tau, and this is called the kernel or the kernel function. Okay. Now we will say that this y of t is uniformly bounded. Okay. So how to prove y of t is uniformly bounded? For you take the maximum value of your kernel function as r. Maximum value of your kernel function as r. Therefore, when you take modulus of y of t, it should be always less than or equal to integral over 0 to 1 maximum of the kernel function, that is r, into modulus of x of tau d tau. Now this is equal to x of tau d tau. We have already assumed that which is less than r. So what you got is this equal to capital R into small r into integral 0 to 1 d tau. So you will when you take this integration, you will get this as tau in between the limits 0 to 1. So you will get it as 1. So this entire integral will become capital R into small r. So what you got is here modulus of y of t is less than or equal to r into r. See, no t term has comes over here. That means this is uniformly bounded. Okay, so it means that uniformly bounded. Now we have proved that your y of t is uniformly bounded. Thus, what you got is the operator k is bounded. Also, y of t is uniformly continuous. Now let epsilon greater than 0 be given by the uniform continuity of kernel of k t tau. There exists delta greater than 0 such that this kernel function we will discuss under the topic examples of linear operators. That section we haven't taken, it seems. Only first example only we have discussed. In your second example exactly this is coming, kernel function. that we will discuss in your coming classes. So modulus of k of t tau minus k of t2 tau, which is less than epsilon by r, for modulus of t minus t2 less than delta, and any tau belongs to closed interval 0 1, which implies, see here, we are having modulus of t1 minus t2 is less than delta. Therefore, take modulus of y of t1 minus y of t2. That's again you can have the integrals notation, and this from this you can combine these two integrals, that is integral 0 to 1 k into t1 tau minus k into t2 tau x of tau d tau. Now this value you have already assumed that which is less than epsilon by r. So epsilon by r has been taken out. Now coming is integral 0 to 1 modulus of x of tau d tau, that's equal to this quantity we have assumed to be as r. So we are getting epsilon by r into r, that's equal to epsilon. So for any function y of t belongs to m is equicontinuous. Thus, by Arcelo's theorem, we can conclude that the set y of t is relatively compact in C of closed level 0 1. What was Arcelo's theorem? Arcelo's theorem says that a set is going to be compact if this satisfies pre-compact if it satisfies two conditions. That is, first one was uniformly bounded or bounded in the C of closed level 0 1. Second one was, it says that it is equicontinuous. So we have proved that two cases here. So we can say that y of t is relatively compact. Hence k is compact. Next is the definition. Let X be a metric space and let a subset of X. A set A subset of X is called the epsilon net of A if for all X belongs to A, there exists Y belongs to A such that the distance from X to Y is less than epsilon. So what this means? This means that you have got a metric space X. So this is your metric space X, and suppose you are having a subset of this metric space as A. Now A subset of X is called an epsilon net if you take an element X over here. If you can find an epsilon neighborhood, let me say it as an epsilon neighborhood because we have taken a metric space. If you can find an epsilon neighborhood and suppose there's some y over here, then we will say that for any point, okay, for any point we can find such an epsilon neighborhood, means we will say that this is an epsilon net of A. Is called an epsilon net of A if and only if for all X belongs to A, there exists a Y belongs to A such that the distance from X to Y is less than epsilon. Now here's lemma. M is relatively compact if and only if for every epsilon greater than 0, there exists a finite epsilon net in M. That is, we want to prove in two ways. We want to prove that is M is relatively compact implies for every epsilon there exists a finite epsilon net, and reversely we want to prove that if there exists an epsilon net, then M is relatively compact. So assume for the first part, let us assume that there exists an epsilon not greater than 0 such that there is no finite epsilon dot net. Now suppose we are having an epsilon value such that for that epsilon value there exists no finite epsilon net. So that means we can take an x1 belongs to M and x2 belongs to M such that this x2 is not in the epsilon neighborhood of x1. That means norm of x1 minus x2 is greater than or equal to epsilon naught. Now select an x3 belongs to M such that again you will have x1, x2. So what you're having is, first you're having an x1 here. Take an epsilon neighborhood, then you can find an x2 outside, right? So this is going to be your epsilon. So x2 is outside. Now you can take an x3 such that when you take an epsilon neighborhood of your x3, this x1 and x2 are not in the epsilon neighborhood of x3. So you select an x3 such that norm of x1 minus x3 and norm of x2 minus x3 are greater than or equal to epsilon naught. Now such an x3 exists since there exists no finite epsilon naught net. Okay, so we can go on this process. Now suppose xi equal to 1 to n minus 1 is selected. So x3, x4, x5, like that we will get a sequence. Then we can have xn belongs to M such that norm of xn minus x1, xn minus x2, etc. xn minus xn minus 1 is greater than or equal to epsilon naught. So after selecting x1, x2, x3, that will satisfy this property. Okay. But can xn exist for every n? Since the reason is, if not, then what will happen? If not, then you are having your x1, x2, etc. xn minus 1 is a finite epsilon naught net. Right? If such a thing is not there, means that belongs to xn belongs to any of this epsilon naught net. That means how many epsilon naught net should be there? N minus 1. So it's a finite quantity. So we can conclude that there exists only finite epsilon naught net, but which is a contradiction to our assumption, because we have assumed that there exists an epsilon naught such that there is no finite epsilon naught net of M. So you got a contradiction. Thus, no subsequence of xn is a Cauchy sequence, right? Thus, no subsequence of xn n equal to 1 to infinity is a Cauchy sequence. Cauchy sequence means when you are having some xn and xm, the distance between norm of this should be less than epsilon for every n comma m greater than or equal to some n. But in this case, you cannot have such a thing, because the distance between x1 and x2 is greater than epsilon 1. Each term is greater than epsilon naught. So it is not a Cauchy sequence, which implies M is not pre-compact. So what you have proved, if M is pre-compact, contrapositive, right? If M is pre-compact, then for every epsilon, there exists a finite epsilon net in M. So M is pre-compact, then for every epsilon, there exists a finite epsilon net in M. Now we want to prove the converse part. Converse part means, what we want to prove? That is, for every epsilon greater than 0, there exists a finite epsilon net in M, then M is pre-compact. That we will prove in our next class. Okay? Thank you for your patient listening. Thank you.